fundamentally, the savings arise from the fact that intermittent electricity is cheaper than fuel. I can run my facility continuously while taking power when it's most advantageous.
This is EnergyCast, and I'm Jay Dowenhauer. Today we're talking about thermal energy storage and how this could be the answer renewables are looking for. We recently discussed this issue in episode 136. Renewable energy may be clean, but it's frustratingly intermittent. And rather than spread energy across the day, more renewable energy typically only creates more excessive supply when, say, the sun is shining. It's also forcing renewable energy generators to dump or curtail as much as 30% of the renewable energy produced. My guest in that episode had a solution. Build infrastructure like data centers that can consume all the excess energy. Today's guest has a solution that works in much the same way, but is far less technologically complex. Rather than state-of-the-art computing, today's guest is heating up bricks much like you'd heat up a slice of bread in the toaster. As he puts it, the cheapest way to absorb electrical energy is a hot wire. They use bricks because they're an affordable and proven material. Just ask steel producers at the dawn of the Industrial Revolution. Together, these heat batteries can get up to 2,700 degrees Fahrenheit, hot enough to run almost any modern industrial application, from steam boilers to kilns to concrete manufacturing. The beauty of this technology is that it can use an enormous amount of energy when there could be gigawatts of excess energy on the grid that need to be consumed quickly. They can also store this energy in a short amount of time for long stretches. The example given was about 4 hours of storage for 24 hours of use. This is great news for renewable producers and utilities who are regularly seeing negative energy prices and even energy curtailments. It's great for industries because they can buy this excess energy at a bargain. And it's great for the eco-minded because you're efficiently consuming all of the renewable energy being contributed to the grid. It's simple solutions like these brick batteries that are a clear path to more renewable energy generation. My guest today is John O'Donnell, CEO of Rondo Energy, a thermal energy technology based in Oakland, California. Rondo has been in the business for about 3 years. They plan to place their first commercial units in service by the end of 2022. We discussed several of the applications and possibilities a thermal battery of this sort could provide. To hear John tell it, the market is huge, and there's not much out there that can solve issues quite like this. I was also happy to contribute an off-the-cuff comparison to this technology that I'm pretty sure they're going to use in their marketing materials moving forward. I hope you enjoyed my conversation with John O'Donnell. We're here with John O'Donnell, CEO of Rondo Energy. And John, this is an interesting technology. It's a heat battery. So describe for us how this heat battery works.
It's a real pleasure to be with you. Rondo's building this thing, as you say, it's called a heat battery. And it's not surprisingly, a heat battery supplies heat. We are delivering zero carbon industrial heat. Industry uses more energy than any other part of the world economy. Not a lot of people know it, but 3/4 of the energy that's used by industry is in the form of heat, whether it's driving a refinery or making baby food or making cement. Heat drives the processes that make all our commodities. Today, essentially all that heat is provided by fossil fuels. Rondo's heat battery is designed specifically to deliver that heat from intermittent wind and solar power, which around the world are becoming lower cost than fuels, and to provide safe, highly efficient, low-cost path for industrial decarbonization where a zero carbon energy source is lower cost than today's fossil carbon source. Our goal with this technology, we selected very simple basis materials, parts to make a heat battery so that we could take it to very large scale, very rapidly, and deliver operating cost savings for industrials, as well as value and profit for the renewables developers who are going to provide that electrical energy and allow us to build a company to open this market.
Yeah. And John, I'm not asking you to reveal any trade secrets or anything, but the website says you're storing the heat in bricks and kind of reminds me a little bit of like sauna rocks or something. So what can you tell us about them?
Sauna rocks. Thank you. I haven't thought about it putting it that way.
You're welcome.
Thank you. I should have talked to you earlier. There are a lot of different ways of storing heat. And it's just in the last few years that what we're doing matters. We go back 5 years. Everything I just said about renewable electricity being lower cost than fuels was wrong. And the notion that we would just store heat from electricity kind of sounded stupid to a lot of folks. But now we're at this moment. The CEO of Intersect Power talked about electrically heated thermal storage as an inevitable trillion-dollar market. We agree, because folks are waking up to the fact that, oh, look, there is a path where we're going to be able to decarbonize industry, storing energy as heat. You don't have the electrochemistry costs and losses of electrical batteries or hydrogen systems. And there are a lot of different materials you could use for heat storage. Concrete and liquid aluminum and liquid sodium and liquid silicon and graphite. There are a lot of very interesting science projects out there that may produce interesting breakthroughs. But there was one really humble, simple thing that had been in use for 200 years, and it's brick. Every steel mill blast furnace has what they call blast stoves that are heat storage units. At any moment at a blast furnace, one of them is being heated by the exhaust from the furnace, and the other is giving up its stored heat to preheat the inlet air to the furnace. And they swap about once an hour. This technology has been in use since 1828. Those blast stoves last 50 years between overhauls. So the foundation is very, very simple, and maybe most important, everything is known about how long these materials last in this service. Because when we're talking about energy infrastructure has to last for decades. And sometimes, as a result, it takes decades for new technologies to be proven, whereas we were fortunate to find a foundation that was already fully proven so that we can go to scale rapidly.
I'm almost a little bit disappointed that it isn't using some sort of new molecule or some rare earth mineral. Please tell me it's more complicated than just using an Acme brick.
Well, yeah, my first job was at a fusion research lab. There are a lot of exciting science projects in energy storage these days. The innovation here, the foundation of the design, the foundation of the patent portfolio was an insight in how to use radiation. The way the sun heats the earth is not by heating some fluid, it's just by light. The rate of radiation heat transfer goes as the fourth power of temperature. We figured out a way to build a brick structure where every brick was surrounded by open chambers that have heat radiation, and every chamber was surrounded by bricks. So it's our structure, this thing we call the radiation echo chamber, that made this practical, but it's not a material. It's just a way of the particular shape in which we've built the systems.
All right, we're back. I was going like, how do you get a patent for bricks? No, this is really exciting. So your website says you're taking heat from intermittent power. And as you explained, it sounds to me like you're really able to ride the level of intermittent power that's on the grid. But as a general industrial customer, they don't usually see that. They just have reliable electricity, right? But you really want to be able to take advantage of the intermittent nature of renewable energy supply is what it sounds like. So it would also sound like you're using some sort of form of demand response, right?
Yeah, thank you. You just put your finger on two or three really big things. Any industrial who's running a natural gas-fired boiler could, of course, install an electric boiler and buy electricity continuously. And if they're in a place where there's wind on the system or solar on the system, 20 or 30% of their energy could be coming from intermittent renewables that was blended with continuous electricity from gas or coal-fired power plants. One of the things about that path to electrification is every new electric load requires more transmission and requires more generation capacity, unless they do some of that demand response thing you're talking about, where you turn it off during hours of peak demand. But demand response means you're turning off your industrial process. And there are a lot of industrial processes that if you turn that thing off, it takes you days to restart it. Demand response is curtailing the end product. This is a whole different deal. We are creating a new kind of load on an electricity system that does not require continuous energy. This is dispatchable generation following load. The grid operator can control it in exactly the same precise way as they control generators on the grid, so that we can exactly time match when energy is being taken to either moment-to-moment energy prices or moment-to-moment energy supply. This is really important for several reasons. Let's look at mid-continent North America. There are 2,000 hours a year right now in Oklahoma of negative wholesale electricity prices. Large-scale industrial heat use of that energy can provide floor prices in that market, tremendously improve profitability for both the renewable and the conventional power providers, and dramatically reduce the energy bill for industrial, in chemicals, in food, and all kinds of industries, and decarbonize those industries all in one go. That intermittent purchase of energy and putting it in very low-cost storage can provide a solution for both the industrials who want to decarbonize and for the developers who want to build more renewables and for the guys who own today's electricity grids. Switchable loads have a huge positive impact in grid resilience and reliability. But unlike demand response, like you mentioned, turning the charging circuits for the storage unit on and off has nothing to do with the product that it's delivering, right? The refinery, the chemical plant, the food production plant gets to operate continuously, even though, it's operating 24 hours a day, but it may be getting all the input energy in 4 hours a day. Those hours might not be contiguous. The grid operator may be deciding when that unit is charged based on wind availability, for example. So this kind of storage is not moving electricity from noon to 7 p.m. to match a solar demand profile. It's capturing energy for this other purpose of industrial heat. And I mentioned before that industrial heat's pretty big. The International Energy Agency did a study a few years ago of it. This year, there was like 2,000 gigawatts of wind and solar in the world today. Repowering the world's industrial heat is going to need 9,000 gigawatts of new generation to provide that primary energy. The early deployments are going to help stabilize today's electricity grids, but we're talking about one of the greatest business opportunities for renewable development in the world of serving this entirely new class of load with renewable energy for the first time.
John, this reminds me a lot of an episode I had a couple back, episode 136. It was Soluna Computing. And what they introduced to my listeners is this idea of curtailed renewables, right? Like we've gotten to the point where we're almost making too much renewable power at certain times of the day. And so his statistic was, I think, as much as 30% of renewable energy has to essentially get dumped. It doesn't reach a source. It just has to go away. And Soluna, what they were able to do is use that curtailed energy to power a really energy intensive process, which was computing, raw data crunching. And so this sounds a lot like that, where you have a huge need for energy. It doesn't have to be on all the time. It can absorb that excess energy and take it off the grid, kind of serves as an accordion. So it sounds to me like you're able to also take care of the curtailed renewable power as well. Yeah.
That's an excellent point. And yes, that statistic was a really good one about what fraction of renewable electricity is curtailed. I referred to negative prices, and those negative prices occur during those periods. And there is a mix of curtailment and negative prices. And in different jurisdictions, the one thing that we can say is that lots more of that is coming. Every one of the studies that as we look in the electricity grid to how do we go from 20% to 50% to 80% renewables in our electricity supply, curtailment grows dramatically because building larger renewables so that during the low wind periods, or the low solar periods, we have enough solar then to carry the grid, means there are periods where there's way more than the grid needs. And again, industrial heat suddenly becomes a giant sink for absorbing what would otherwise be discarded renewable energy that's directly one-for-one replacing fossil fuel use. But as I mentioned, the actual total energy demand is much larger. Industrial heat is going to cause construction of lots more new renewables beyond that. But in the early deployment, for sure, absorbing what is otherwise curtailed, wasted power is an important piece of value.
One of the things that Saluna and I also discussed was this idea that if you curtail 30% of the renewable energy, that's also 30% of the renewable energy credits. For every megawatt hour of renewable energy produced, you can also sell a renewable energy credit. So you're missing out on about 30% of those available renewable energy credits that could have been sold. So that's something that makes you guys a hero.
Indeed, that is absolute value creation as well. But when people talk about 30% of the energy being curtailed, that's true. The question is, when does it happen? The time periods during which curtailment occurs tend to be fairly short. You may have 8 or 12 hours of solar generation, but 1 or 2 hours of curtailment. So the question is, if you want to pick up that 30% of the energy, you have to be able to do it at a very high rate for very brief periods of time. And as a result, the big question is, what does your thing cost per kilowatt? You want to absorb that energy, but you're only getting it in 2 hours a day, and you're not getting it every day. And with a lot of equipment, consider hydrogen electrolyzers, or for that matter, data centers, the capital cost of the equipment that's going to use that curtailed electricity, if you're not running it very many hours of the year, it's a cost that's one of the limits to why this isn't already happening. As those costs come down, they fit more. One of the unique things about what we're doing at Rondo, the way we absorb energy is with electrical heaters that are the same material as in your toaster, and arguably the absolute cheapest way of absorbing electrical energy is a hot wire. Our technology is very well suited to high rate charging for brief periods, which is what you really need to do if you're going to absorb curtailment significantly.
John, going back to the technology itself and its place in an industrial setting, is this absorbing heat from other processes in the facility similar to a heat recovery unit? You're not just drawing power off and heating up. I mean, there's a lot of residual heat all over a typical factory.
Yeah, that's a great question. And, that's an area that's getting a lot of attention, especially today. Waste heat recovery, recapturing heat that's maybe lower temperature at the end of a process and putting it to use. We've had very interesting conversations with some of the innovators in that area in combining that low temperature waste heat with high temperature stored heat so as to raise the efficiency with which that low temperature heat can be used. Waste heat recovery is challenging because it's low temperature. You have to move a lot of air or water around to move that low temperature heat. We are exclusively focused on providing the high temperature input heat to the industrial process, but we're seeing a lot of interesting innovation in how do we combine that with waste heat recovery to further improve the overall economics and energy efficiency.
Yeah, I had a guest one time who was able to do warm water heat recovery. It was a Swedish company called Climon. Yeah, we know the same people. Is this any way related to combined heat and power unit? Another episode I did was episode 24 with a company called Capstone Turbines. Those are micro turbines and obviously powered by natural gas, for instance. But is this in some way combined heat and power?
Everybody who took their electrical engineering or mechanical engineering in college, combined heat and power gives you the optimum thermodynamics. When we convert heat to electricity, there's a lot of lower temperature heat left, and combined heat and power systems, instead of being 40% efficient, can be 85% efficient because they use that lower temperature heat. Rondo systems deliver heat at a very high temperature, and delivering combined heat and power power. For example, making high pressure steam, driving a steam turbine that delivers continuous electricity, and then taking lower pressure steam from that turbine to drive an industrial process. Actually more efficient than fossil fuel fired combined heat and power because there's no exhaust stack. Combined heat and power down this track is 95% energy efficient, and it's a really important piece of overall the energy transition for industrial processes from fossil energy to continuous electricity and continuous heat from an intermittent source. So yeah, and you mentioned microturbines as one of the highest efficiency, simplest way to do it with fossil fuels. That's absolutely right. We believe we are the simplest, highest efficiency way to do it with intermittent renewable electricity as the input.
These industrial processes are going to need essentially the same amount of heat. And what you're doing is you're kind of acting as the accordion here, and you are using renewables. And you say you're saving on energy costs. How does that work? They still need the same amount of energy, I would think, to heat. Do they get those savings from variable pricing, pulling from the grid? When prices are low, you're able to absorb a lot of those renewables. Help us understand the economics there.
Yeah, thank you. Now, energy economics are local, right? They're different in different places in the world. And when we're talking about heat, we're also talking about direct CO2 emissions, scope 1 emissions, which in some places in the world also have a carbon price associated with them. In some places in the world, there's a fuel price and a carbon price that's associated with today's heat supply, and switching to renewable electricity eliminates both of those. In other cases, places in the world, there is no carbon price. And it is, as you say, what's the electricity price versus the fuel price? If we look at mid-continent US today, natural gas prices that if you do a units conversion result in a cost of heat of about $15 a megawatt hour of heat. Before the current geopolitical, it was maybe 11. If you were able to participate in wholesale electricity markets, you'd be paying more like $18 or $20 a megawatt hour for that electricity. It would never make sense to install an electric boiler. But if you had a storage unit that bought electricity only in the cheapest 4 hours a day, every day of the year, your annual average electricity price in North Texas in 2020 was about $1.20 a megawatt hour. In other places, it's about $4 a megawatt hour. In some places, it's negative. Right now, with no carbon price, the opportunity, if you can participate in these markets with an energy storage unit that only buys in the cheapest time period per day, you can have a dramatically lower cost of energy right now without considering what the carbon value is. So that's being a price taker in markets. But in every one of those places, there is also this unique opportunity because of where we are with the wind industry and the solar industry. Developers will be happy to build new solar facilities and wind facilities so that you can stop being a price taker. You can contract for 20 years for a fixed electricity price. And whether you're in Saudi Arabia or Canada or California or Australia, you can have fixed electricity prices on a long-term PPA that are well below your current cost of energy. The answer is a little bit local, and it does depend on local renewable energy dynamics. But fundamentally, the savings arise from the fact that intermittent electricity is cheaper than fuel or fuel plus carbon, depending on where you are.
Got it. I kind of thought that it might have something to do with being able to take advantage of time of use
yeah,
consumption.
Absolutely. That's right.
And you can do that because you don't have to have it on matching 1-to-1 when maybe the facility is rolling hot and heavy.
That's what storage does for you, exactly that. Now, it's time of charging when I'm taking the power, not time of use. I can run my facility continuously while taking power when it's most advantageous.
In episode 105, we discussed district energy networks, Vicinity Energy. They're a pretty large operator for that. Your website would suggest this technology is ideal for industrial purposes, but what about campuses or commercial buildings? And what about using these hot bricks, if you will, to maybe fire up pipes and transport heat around maybe like a campus?
Yeah, thank you. My goodness, you're asking all the right questions. There's been a lot of focus in these district heating systems in how can we decarbonize them? They're a very interesting opportunity. And how can we reduce their operating costs? A lot of the focus recently has been on using heat pumps to gather electricity and deliver heat. Most of those district heating systems were carrying heat around in the form of steam because steam has high energy density. Switching them over to run hot water on heat pumps often involves replacing most of the heating system. 6-inch pipes get replaced with 36-inch pipes. Each building that's attached has switchover. What we're doing actually does very cost effectively repower those district heating systems without touching the system at all. You continue to use steam to move things around. None of the campus changes, but instead the burner or the turbine that's running the boiler today is the only thing that's replaced. And the transition to zero carbon is much lower cost. As we said earlier, and you just said it, we have been exclusively focused on the industrial applications because they are very large energy consumers. We did decide to build a smaller version of the heat battery specifically to address some applications as you're speaking. So we actually have 2 models of the heat battery, one that's somewhat smaller that appears to be a good match for district heating systems.
And then finally, where is Rondo at this point? Are we commercial? Are we selling now? You talked about developing the battery, so just checking to see where we are.
So we're commercial this year. And last year, we raised a round of financing that was jointly led by Bill Gates's Breakthrough Energy Ventures and Energy Impact Partners, EIP's Decarbonization Fund. Their investors are the electric power industry. And not surprisingly, down the track where we're electrifying everything, the electric power industry is going to be really in the center of that. That funding allowed us to move from the laboratory into delivering our first commercial units. We're delivering our first commercial units this year. We're in manufacturing and construction now and look forward to talking to you about them when they're online.
All right, John, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
We are now at a point where natural gas is more expensive than intermittent electricity. So we are in a transition to natural gas being something that provides swing capacity, it provides seasonal fill-in, and that industry is going to play a role in backing renewable energy and transforming itself in other ways.
Crude oil.
We're going to see more energy moved over electric wires and less as molecules as the world goes forward.
Nuclear.
The nuclear industry's biggest challenge that I see as an outsider today is scaling up and scaling up at a price point.
Coal, and I'll add coal with carbon capture.
I spent a little while as a VC looking at carbon capture technologies. The fact that I'm doing what I'm doing right now tells you something about my skepticism about how deeply and quickly we can bring carbon capture to scale and have it be economically beneficial. Carbon capture raises the cost of energy supply.
Wind.
The wind industry has brought their cost of energy down, 98% in the last 15, 20 years? They can't possibly continue to come down in cost. And yet every year, there are more efficient gearboxes and bigger turbines and other innovations. I hugely admire what the wind industry has done. It's just amazing.
Solar.
Solar energy is becoming the cheapest form of energy in human history. There are no material or land or other supply chain limits that fundamentally block us from this lower cost, zero carbon world because of what the solar industry has done.
Biofuels.
We are in a world today where biofuels I see as an important bridge fuel to fully synthetic fuels, made from hydrogen from solar energy and from CO2 from some source, including a biological source.
Hydroelectric.
Hydro is severely challenged by what's going on with changing rainfall patterns. The low-hanging fruit for hydro installations was picked a long time ago. We don't see them as the growth path.
Geothermal.
I've been really amazed at the rate of progress in bringing technologies over from the oil and gas industry for enhanced geothermal and accessing geothermal resources that were otherwise unavailable. There are places where geothermal is the anchor and it's the foundation. And then there are other places where the resource is too expensive.
Energy storage, you guys.
There's a diversity, there's an extraordinary explosion, and they're solving an enormous problem and going to scale as fast as they can. We are absolutely in a moment where energy storage is tremendously broadening the opportunities for renewable energy developers, for consumers, and for literally saving the planet.
Energy efficiency.
We are reaching a point where that low-hanging fruit has been picked. It's important to go pick that fruit, but that's how you get 5 and 10% decarbonization. Transforming the fuel source is how you get the other 85 to 90%.
And then finally, fusion power. You actually mentioned you did this, right?
My first job after college, I was building computer systems for tokamak fusion research. It has continued to recede into the distance and to be questionable about can it economically compete. But I'm thrilled that there's been a resurgence of private capital driving the industry, real progress. It's a great moment.
All right, John O'Donnell, Rondo Energy, thank you so much for your time.
Jay, thank you. It's a great pleasure speaking with you.
That was John O'Donnell, CEO of Rondo Energy, a thermal battery developer based in the Bay Area. Granted, they're only about to start commercialization, but John says they want to get to 1% of world emissions within a decade and 15% of those emissions in 15 years. As a testament to the brick material being used, John says they'd consume less than 2% of the world's cement plant capacity, making the storage materials for these batteries. I want to thank John for his time, as well as Melissa Newman at Bospar for setting this up. You can find plenty of pictures on energy-cast.com, as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 148. Be sure to join us next week when we learn how one company bet their future on getting more mileage out of lithium. Until then, I'm Jay Dowenhauer. We'll see you next time.